Okay, now we're going to have Dillon tell us about learning to plan over symbolic world models. And he's at University of Toronto. You can check out some of his previous work, and his website is here. Okay, take a picture of this if you want. And again, multiple places you can ask questions at, and people do. So can be in any of these places, and we'll get the questions. All right, and the last Neuro-Symbolic Wednesday before we do a short summer break before the summer school of about a month is next week. And it's about NeuroLens. Okay, and without further ado, take it away, Dillon.
Yeah, sure. Thanks, Alex. Thank you for giving me this opportunity to present my work. So again, the title of this talk is Learning to Plan over Symbolic World Models, specifically for embodied AI using the technique of goal regression. So first, I'd just like to quickly thank my collaborators, Till Hoffman, Torren Claassen, and Sheila McAraith on the works I'll be presenting today. So yeah, I'll be presenting 2 papers today. One was published at AI, and one is currently preprint. And yeah, so today we'll be talking about planning. So if we ask Gemini what planning means in AI research, we kind of get 2 answers. So there's the problem, or like the planning problem, which is at a very high level, a goal-oriented sequential decision-making problem. And there's also methodologies for solving planning problems, which generally requires reasoning about future consequences of actions. And planning has many kind of applications in industry, AI in general. So at least in embodied AI, we can use it for space exploration, disaster response, and household assistance. So more formally, we can define a planning problem algorithmically as a set of inputs and outputs. A planning problem is given as a set of states, a set of actions which define transitions between the states, some initial state, and a goal condition. And we say that any state that satisfies a goal condition is a goal state. And generally with planning, we want to find either a plan, which is a sequence of actions, or a policy, a goal condition policy that achieves the goal from your initial state. And we may optimize for one or more cost or reward functions, and we may possibly be subject to some state or trajectory constraints or preferences. So we usually also can view planning as just a search problem, because a planning problem induces a graph where we want to find a path from the initial state to a goal state. And search spaces generally grow exponentially with respect to either depth, breadth, or complexity. So with depth, we may kind of expand the search space by finding longer horizon problems requiring many more steps. We can also increase the search space by increasing breadth, which may arise from being able to apply many possible actions in a state. So this may arise due to having like cluttered environments or many objects that you can manipulate. And you may also have more complex search spaces. So for example, you may have dynamic or stochastic environments. You may also have like partially observable environments where you need to reason over belief states, and also open world environments. But putting all these formal definitions aside, we as humans generally can plan all the time in very, very large state spaces without much effort. So for example, with cooking, the goal is, you want to be full, and you may want to optimize for like different metrics such as taste, healthiness, and cost. Yet generally, we don't really take much time to spend when we're cooking. And similarly with commuting to work or like planning a trip or vacation, you may kind of need to consider different modes of transports and roads to take for commuting. And the physical world itself is a very large state space, Whereas in planning, there's also a combinatorial nature of deciding many different places to stay or visit, modes of transport, and again, you may consider different preferences or constraints on your budget. So in this talk, we'll ask the question, how do we plan efficiently? How can we get AI to plan efficiently like humans? And our claim is that simply we use experience and reasoning. And more specifically in this talk, we're going to talk about learning to plan over symbolic world models with a focus on AI and embodied AI with the key technique of goal regression. So here, learning corresponds to experience, and we're going to use symbolic world models for reasoning. And this talk will be split into two parts corresponding to the two papers I'll be talking about. The first part will be talking about symbolic world models and how we can use them to provide structure for fast, high-level symbolic planning. And the second part of this talk will be talking about how symbolic world models can provide useful abstractions to guide low-level open world planning, such as in robotics. And key to both of these papers is a very cool neuro-symbolic or symbolic technique called goal regression, which we'll get to soon. But first, I'll kind of define or set the stage of what I mean by planning with symbolic world models. So there's kind of two components here. There's the world model, and there's also symbolic as the adjective. And in the current literature, what a world model means is simply a function which takes input as an action and state and predicts what the next state is when you apply the action in your state. And for symbolic, what we mean is we're going to use formal languages for representing this world model. Specifically, we're going to use what's known as PDDL, or the Planning Domain Definition Language. And what we do here is that we represent states as relational databases. So for example, here you have facts representing the dog is at the kitchen, the dog is hungry, the cake is in the bedroom, and your robot is in the bedroom. And key to these symbolic world models is the usage of these actions, which are reusable and may have consider symbolic preconditions and effects. So here we have a parameterized reusable put down action, which is parameterized by objects and locations. And the precondition consists of the robot being at the location that it's instantiated at, and it's holding the object. And you have to add and delete effects, which give the kind of intuitive effects of placing the object actually at the location, making the gripper free of the robot, and also deleting the fact that the robot is holding the object. And going back to the planning problem we defined earlier, again, the objective is to find a sequence of actions or policy that achieves a goal condition. So for example, we may have your initial state given by the state above, and you have a goal condition consisting of the cake is at the kitchen proposition. So what will happen is that you may try to find a plan where you pick up the cake, you move from the bedroom to kitchen, and you put down the cake at the kitchen. So a very simple example. So with symbolic world models kind of defined and aside, we'll talk about how we can use them to do very fast, high-level planning, so planning over abstractions. And our problem we're going to look at is learning symbolic policies that generalize from small problems into new testing or unseen problems. So the inputs are given as, a finite set of training problems, and you're also given a symbolic world models, which is, again, a set of reusable actions, such as this put-down operator here. And the output is that we want to learn a policy that solves a set of testing problems, possibly unseen, using this symbolic world model. And in this part of the talk, we'll be using policies that are symbolic, represented as first-order condition action pairs. So symbolically, they look as follows. There's a left-hand side and a right-hand side of the action split by the arrow. And what it consists of is your reusable rules, where it's instantiated by variables x, which we want to find that satisfies a condition on the left, and actions that we apply on the right. So if we split this policy down, we can split it into a state condition, a goal condition, and a sequence of actions. And next, we'll talk about how we actually learn these policies and execute them. So there's several ways we can use learn policies, but in this paper, our key kind of silver bullet is this very old technique of goal regression. So goal regression was introduced several decades ago by Waldinger and also Raymond Rito. And it's a symbolic rewriting technique that computes the minimal and sufficient set of features for achieving a given goal via an action. So what I mean here by minimal and sufficient set of features, we can view this as analogously to kind of attention in transformers, where we want to only find features that are relevant for your task at hand. And here we defined the regression operator for symbolic world models earlier. And it's defined in kind of 2 steps. So given your goal and action, what you want to do is undo the action effect and add the pre-image of the action. So at a very high level, what we're simply doing is computing a pre-image of the goal under this action A. So with goal regression defined, we're introducing our next kind of approach to synthesizing and learning policies from our training set. So recall that our policies take a form of a set of condition action rules as follows. And we're going to synthesize or learn them in 3 steps. So first, like given your set of training problems, we're going to explore and compute kind of a data set consisting of optimal plans for singleton goal atoms in any order. And next, given these optimal plans, we can use our goal regression operator upon these goals and the corresponding plans to get a set of kind of partial state macro action pairs. And then we inductively generalize these pairs and goals into a set of first order rules. So that's the textual description of it. I'll just step through it again visually. Excuse me, with this approach. So again, suppose we have like a symbolic world model. So we're given a set of reusable symbolic actions, such as a put down and a move operator here. And then suppose we're also given training problems. So usually this is defined as a symbolic world model, as well as an initial state and the goal condition. And in the first of 3 steps of our approach to learning policies, what we do is we try to find a plan that progresses the initial state to a goal state that satisfies the goal condition. So as earlier, we've seen that we have the robot in the backyard holding a cake and a dog at the kitchen. So with this state, what we do is we apply the move from the backyard to the kitchen, and then we put down the cake when we're at the kitchen. And then this will satisfy our goal. So then our next step is that given the sequence of actions of moving and then putting down, we regress these actions from the goal condition, and we'll get the following regressed states. So from the cake is at the kitchen, after we regress the put down operator, what we do is undo the action, and now we're holding the cake and the robot is at the kitchen. And similarly, when you regress over the move operator, the cake is still being held, but now the robot is in the backyard. And kind of the key idea of goal regression, again, is that we only find relevant features. And this regression now deems that actually, the dog being at the kitchen is kind of irrelevant for solving this problem or like for learning a policy here for these kind of goals. So the final step of this approach is we generalize these regress states into rules. So we can kind of map certain components of goal conditions, the actions, and regress states into parts of the rules. And then we lift the kind of objects. So for example, the cake is now a reusable variable object, and similarly the kitchen as a location. And we do this with every regress state. Okay, so now we've learned how to learn these policies. So what we want to do now is execute them as policies. And again, we can do this in 3 simple steps. So given a new problem, what we want to do is, as with any kind of policy execution, we set a state to your current state. And while your goal is not being achieved, you repeat the following steps. First, you want to ground a rule where your state condition holds in the current state and the goal condition holds in the set of yet to be achieved goal conditions. And you simply apply the corresponding sequence of actions on the right-hand side of the state of the rule if the condition is satisfied. And the key idea here is that we can kind of implement this algorithm using first-order database query algorithms such as SQL. And so now this gives us the Moose symbolic planner. So we have goal regression for learning rules and policies and database algorithms for executing such policies. And moving on to experiments, we want to answer the question of, okay, does our approach, how well does our approach, scale? And by scaling, we mean in terms of solving speed and solving problem size. And with the experimental setup, what we do is we look at 12 different combinatorial polynomial time to solve planning domains, consisting of training and testing splits. And with the number of training objects is usually very small, while our testing problems can be orders of magnitude much larger. And we're going to compare against like the strongest state-of-the-art symbolic planners in the planning kind of literature. And we're going to try to measure the number of problems we can solve within a given compute budget. Specifically, each planner is given 8 gigabytes in memory and 30 minutes of runtime per problem that needs to solve. And here are the results. So the plots we're looking at are cumulative coverage plots. So to read these plots, what you're given is, in a given XY point, the y-axis denotes the number of problems that the planner solves within the x-axis amount of times. And a very high level kind of way to read this plot is that higher values are better. And notably also, the problem search space usually scales exponentially, so each problem gets exponentially more harder to solve. Yet when we look at these plots and we're comparing to state-of-the-art kind of numeric and propositional planners, our Moose approach just very strongly against the state-of-the-art and solves almost all problems after learning in very short amount of time. So we're actually not done with this first part of the talk. We can actually have another contribution, which is that we can use these condition action rules to guide search. And we're going to use these rules by guiding search in terms of pruning the search space, so we can search fewer places. And we're going to use this key idea of PDDO axioms. So axioms are simply additionally derived state features given your initial state. And what we can do is we can encode axioms that detect unachieved goals. So when a goal is not yet achieved, we can encode an extra feature to say that it's unachieved. And next, we can also encode axioms that restrict action application based on the learned rules. So in this way, we can restrict the number of actions that we can apply in any given state. And the good thing about this approach is that this approach scales in terms of the state of the art, because we can simply feed this transform problem into any PDDO planner that supports axioms. So our Moose symbolic planner actually consists of 3 components now. It kind of learns rules by goal regression. And these rules can either be used as policies or also for search to prune the search space. So again, we're going to ask the question, how well does Moose scale, but now for search? And to answer this question, we now look at kind of NP-hard optimal planning domains, where we now require search where policies may not be sufficient to solve these problems. And again, we're going to compare with state-of-the-art symbolic planners and use a similar metric. And here are the results. Again, we're looking at cumulative coverage on the left-hand side, and our approach does a lot better than kind of the state-of-the-art for optimal planners. And when we also look at the right-hand side, we're looking at coverage based on every domain. And what we're trying to see is if this Moose approach of encoding axioms to prune search improves upon the base planner that uses Axiom. And to look at this plot, we use SimK as the base planner, and we see that almost always this Moose approach improves upon the base planner. Okay, very good. So that's the first part of the talk. So we've been using goal regression and symbolic world models to do very fast, high-level planning that can solve problems with several thousands or tens of thousands of objects in a high-level abstraction. And now we're going to talk about how we can actually use these symbolic world models and goal regression to also guide low-level planning. So we may want to, construct AI or robotics or embodied AI that can solve problems in the real world, where we now have continuous actions in state spaces. So the question we may ask first is, what exactly is the state of the art for embodied AI? And a good way to kind of answer this question is we'll look at this Momo Spaces benchmark created by the Allen Institute of AI, or AI2. And this consists of many environments, robots, objects, and grasps, and also various different simulation environments, such as Isaac, Jim, and Majoko. And they have a running leaderboard where different kind of systems can be submitted to solve these benchmarks. And the main takeaway here is that there are kind of two major paradigms for embodied AI. On the left-hand side, you have the big scaling learning approaches, where we have vision language action models, reinforcement learning, diffusion policies, and flow models. So we've probably seen many demonstrations online of these approaches, and they exhibit really strong low-level capabilities from learning from diverse data sets. But it's generally considered that these approaches are very expensive and cannot solve long horizon planning tasks. On the right-hand side, however, we have more classical robotics algorithms. So we have some combination of perception, localization, and manipulation, and then some tasks and motion planning. And yeah, generally these classical robotics algorithms are complementary to learning approaches. They can solve kind of long horizon planning problems quite well, but they're generally quite brittle to uncertainty and open world environments due to reliance on perception and learning models, or using models to plan. And on the top right corner here, we see the top three kind of approaches on the benchmark. So in March, this classical robotics approach, TipTop from MIT and UPenn, was actually first and solved most of these problems quite well. But more recently, we see that the learning approaches kind of overtake them earlier this month. So our proposal in this second half of this talk is, okay, let's combine the best of both worlds. So we have the neural part of learning and the symbolic part of classical robotics. So so like in Neuro-Symbolic Wednesdays, we're going to do some neuro-symbolic stuff. And we're going to combine learning and classical robotics. And we claim that this gives us, the strong low-level capabilities by learning from demonstrations from learning. Also, you have like robustness to uncertainty and open world environments from learning policies. And by the usage of classical robotics and symbolic world models, we can also solve long horizon planning problems. So to recap, we're going to use learning for manipulation and control. Secondly, we're going to use our key ingredient again of goal regression for robustness. So if we recall, the idea of goal regression is that we extract the minimal and sufficient set of features, which gives us more robustness to solving tasks at hand when we have uncertainty and noisy perceptions. And again, we're going to use symbolic world models to help do some long horizon planning. So the approach and talk structure of this remaining part is as follows. We're going to talk about our problem statement. Next, we're also going to talk about how we represent states and actions and the environment for robotics problems here. Third part, we're going to talk about data set extraction. And finally, we're going to talk about policy representation and learning. So noticeably, our approach is a bi-level or hierarchical approach for planning. we'll have a high-level policy for doing some high-level planning, and we'll have a low-level policy guided by our high-level policy and abstractions to do your low-level manipulation and control. So what's our problem statement? We're going to learn from demonstrations using symbolic world models to solve new and unseen testing tasks in robotics kind of problems. So we're going to assume that we're learned or given in symbolic world model. Here, D represents a symbolic world model, and L represents a mapping that maps low-level states to high-level symbolic states in D. And there's a lot of work that's looking into learning these symbolic world models using either neuro-symbolic approaches or kind of foundation model approaches. And we're also given a set of demonstrations. So these demonstrations are tuples consisting of low-level states such as images or object-centric features or LiDAR kind of scans. And also high-level goals such as, given by text. For example, you may tell the robot to clean the table or to pick up the mug and put it somewhere or take out the trash. And we'll have low-level actions. So this corresponds to just the motor or manipulation control of the robots. And our objective, given these two components of world model and a set of demonstrations, is to learn goal condition policies that generalize to new problems. So by generalization, we mean to different or more numbers of objects, different goals, and also different states. So given our problem statement, we're going to next move on to our state representation. So our inputs are usually low-level kind of representation, state representations combined with some high-level goal that could be a textual description. So low-level states can generally be like image, video, or LiDAR. And next, we're going to assume that we can use existing perception or CV tools to kind of extract object-centric representations from our low-level inputs. So given a scene, we may try to extract where all the blocks are, trays are, and grippers are, and we kind of can compute their depth and also location and rotation properties. And given these two low-level inputs, we can also assume existing work that learns a symbolic world model that maps low-level states into high-level states. So the high-level states, again, are represented using databases or kind of the PDDL states that we've seen before. And these simply correspond to abstract symbolic facts. So next, with the state representation aside, we'll talk about how we extract additional high-level information given our low-level demonstrations and symbolic world model. So if we recall, we're only given a set of low-level demonstrations with high-level goal instructions as the dataset. And we can visualize them as follows. We have high-level goal represented in the rectangle, and we have states in circles and the actions that kind of progress states into the next states. And what we want to do is we want to extract additional set of high-level demonstrations from what we're given. And we're going to use these high-level demonstrations to next learn a high-level policy. And the key idea is to do this, we simply iteratively find high-level actions that explain transitions between different low-level states. So in more detail, what we want to do is we first map these low-level states into high-level states, and then we find kind of actions that satisfy the precondition and also explain the add and delete effects of the transitions. And again, we're going to use database query algorithms similarly to how we were executing policies as before. So with dataset extraction aside, we can now move on to policy representation and how we can learn policies given our both low-level and high-level demonstrations. So from our low-level demonstrations, we're going to learn a low-level policy that's neural. and a high-level policy that's symbolic. And for the high-level policy, we will just reuse our approach from part 1 of this talk with some minor additions and extensions to handle non-deterministic and open-world environments. But the main takeaway is that these high-level policies are symbolic policies, again, consisting of symbolic conditions and actions. And key to our approach for the low-level policy is that we're going to learn a very lightweight, small 30,000 parameter model. So I'll quickly next talk a bit more about our low-level policy architecture. So we can visualize it as a message passing neural network operating on the object-centric states as follows. And the inputs are on the left and the outputs on the right. So the inputs are corresponding to the form of our low-level demonstrations. So we have a low-level state, and we also have a high-level goal. But furthermore, we also have a high-level action, which we assume that we've computed using the high-level policy that we've synthesized. And going back to our data set, these high-level actions can also just be extracted from low-level demonstrations. And simply what we want to output is one single low-level action to apply given any state and goal. And in this architecture, we assume that we have object-centric embeddings again. But furthermore, we also use large language models to embed the textual components of the symbolic one models. So for example, we have our pickup action, which we can embed with text. And we also have additional facts and predicates in the state, which we can also encode. And the reason for doing this is that we can learn just one single architecture that operates for arbitrary symbolic word models, since we're now operating over text space. So to summarize, what we have is now our Bison approach for learning bi-level robot policies, consisting of a low-level policy and a high-level policy. So our low-level policy is a very lightweight, object-centric foundation model, where we can learn a single model that encapsulates different skills and can work for any environments. And we also learn a high-level symbolic policy, similarly to part 1 of this talk, which is interpretable and symbolic, and can elicit long horizon planning. And another key benefit with our approach is that with our bi-level kind of approach, it is very modular in the sense that we can interchange our high-level policy depending on different tasks and goals. So now we'll move on to some experiments. And the goal of our experiments is to evaluate how well our approach, our robot policies generalize to long horizon tasks, and also how robust they are to uncertainty. So recalling the two paradigms in embodied AI, VOA and neural approaches still struggle to solve longer horizon tasks, whereas more classical robotics kind of struggle with uncertainty and open world environments. So what we do is we're going to set up experiments as follows. We're going to look at 4 different stochastic environments in simulation, and we're going to provide our approach with 200 demonstrations per environment. And what we want to do is train with environments with only up to 3 objects and evaluate them between 1 to 10 objects. And we have set up various different baselines ranging from VLA to end-to-end and also classical robotics baselines, but we'll defer these details to the paper. So the first part of our experiments tries to look at how well Bison generalizes to long horizon tasks. And here we simply plot the success rate of our approach on solving different problems relative to the number of problems in the environments. So recalling, we train only up to 3 objects, and we try to test and evaluate to 10 objects. And we see here that Bison generalizes to longer horizon problems relative to our end-to-end baselines. We also view that VLA baselines even struggle with our benchmarks and solve almost no problems. another takeaway of our approach is that, again, our approach is more robust to uncertainty and open world planning compared to other symbolic classical robotics planning baselines, which need to do a combination of execution monitoring and replanning. And we see here that, again, our approach favors very well to such environments compared to kind of replanning and classical robotic algorithms. So that's it for my talk. Here's our summary slides. So we've talked about how we can learn to plan over symbolic world models for embodied AI using the key technique of goal regression. So we talked about our Moose architecture, where we use goal regression to synthesize very compact and symbolic rules as policies or for search, which outperform the state of the art by orders of magnitude, several orders of magnitude. And we also talked about how we can learn bi-level policies using symbolic world models and goal regression to get some long horizon planning that operates quite well over both uncertain and open world environments. And yeah, that's the end of my talk. Thank you.
Okay, thank you very much for your talk. Very interesting. We have a couple of questions from YouTube. How to find the PDDL rules? This will have its own computational complexity besides search using PDDL rules.
Sorry, can you repeat the first half of the question?
Yes. How to find the PDDL rules?
Okay, how to find the rules. So in our paper, we assume that they're either learned or given. So usually these rules are either given by like a human that has a good idea of what we want to solve, or we can also try to learn them kind of automatically in the case that we don't have a human to give them to us. And yeah, there's a lot of work that kind of looks into how to find these PDDL rules or world models. It's generally quite like a computationally like hard task in practice. There's some papers that kind of look at the worst case scenario of learning these rules. They can be quite intractable. But the current experiments and literature show that current algorithms can learn them quite well actually in practice.
Mm-hmm. Thank you. The next question, I think it's related. So it learns from demonstrations. I think based on what you said, it's not. So the question said it learns from demonstrations. I think it's follow up to the previous one. So it sounds like it is not, right?
Well, we're still learning from demonstrations. So like we're given kind of states and actions that correspond to the actions we want to apply in the demonstrations. Mm-hmm. And then given like these symbolic world models, we can extract a high level kind of model. So I guess like we're not really learning the model from the demonstrations, but we're still learning the policies from the demonstrations. Mm-hmm. Because we assume that there's like already quite a lot of existing work that learns these models.
Okay, thank you. The next question is, a neural network cannot represent first order logic, even if it is a graph neural network, right?
Yes, that's correct.
Mm-hmm. Just propositional logic.
Yes. But the main idea of our approach, oh, sorry, was there more to the question?
No. Sorry.
Okay, yeah. I guess the answer to that comment is that's the reason why we look at kind of high-level policies. So the high-level part of the policy does the kind of reasoning over first-order logic that actually computes the action we need to apply in the high-level space. The low-level policy simply just instantiates the low-level policy, high-level action in the real world. So the low-level policy, the neural network, that's not actually doing any first-order reasoning. What it does is it takes the given high-level action and just simply executes it in the low level.
Mm-hmm. Okay, thank you. The next question is, great talk. Where does the Bison approach come on the benchmark for embodied AI that you showed?
Good question. It doesn't come on the benchmarks yet. There would still be a bit of work to do, such as handling the model learning and perception to add it to the baselines.
Okay, and by the way, very cute pictures of moose and bison. It's just my own comment. Okay, the next question. What is the current bottleneck in topping the leaderboard?
That's a good question. I haven't actually looked at the leaderboard too much, but I guess I can answer for more general kind of like robotics benchmarks. I think the main bottleneck is mostly, I believe it's mostly in the low level, because there's still a lot of like different low level manipulation tasks that's kind of hard to do for robotics. And personally, I believe the high level kind of planning is the easy part for robotics. So this is like Moravec's kind of paradox. We've seen so many times that the AI algorithms are really good at kind of high level reasoning. We also see that LLMs themselves are quite good at like high level reasoning as well. So the bottleneck is, how do we kind of ground our high level reasoning or like actions to the low level space and actually like execute and manipulate them properly. So I think the bottleneck is still in the neural part of these systems actually, rather than the symbolic parts.
Mm-hmm. Okay, thank you. How do you decide which aspects of the agent are learned versus designed symbolically? Do you arrive at this split empirically, or is there a theoretical principle behind it?
Sorry, can you repeat the question again?
Yes, sorry, and just a comment for our technical side for Joe and Ken. Maybe you can show the questions on the bottom while I read those. Yeah, so here is the question. How do you decide which aspects of the agent are learned versus designed symbolically? Did you arrive at this split empirically, or is there a theoretical principle behind it?
Yeah, that's a good question. So with this approach, again, like the symbolic aspects of the agent are kind of assumed to be given or learned like properly, and we also assume that like it's a very good abstraction. So generally we assume that these models are correct, but the level of abstraction kind of defines how useful it is. For example, you may have like a pickup action for picking up mugs off the table, but you may sometimes want like more refined actions. Like sometimes your mug may have a handle, and you may want like more refined kind of high-level actions, such as like pick up the mug from the handle. But again, yeah, to answer your question, I think this is still kind of unsolved and difficult question to answer, because there's a lot of different ways we can try to learn an abstraction. So like how we want to learn an abstraction is kind of underexplored in the literature. So this is more just like something we did. Yeah, we arrived at this split kind of more empirically rather than theoretically.
Mm-hmm. Thank you. I think these are all questions from the audience so far, unless I missed anything. But I have a question, so not sure if I missed it, but I'm curious, what are next steps in your research for both? Like maybe for you or for other people in research who got interested in it, or what are the next directions do we see? And maybe related one, what are maybe the drawbacks of your approaches, and what are the most promising directions? Maybe low-hanging fruits, or maybe even not, maybe some interesting big questions or directions for research you see for yourself personally or for other researchers.
Mm-hmm. Yeah, okay. So like, I guess future work and drawbacks. I think some of the questions like give a lot like future work already. So like, again, one of the major assumptions we made in our second part of our approach is that we're given or learn these symbolic world models. But it seems that most people are not yet convinced that these symbolic world models can be learned in a very simple and scalable way. Most of the works are still kind of done in like controlled environments, but they haven't really been actually evaluated on like third-party benchmarks. One exception to that is like the tip-top paper that I mentioned that came third place in the MoMA spaces kind of work. But even then, they assumed like some prior with the symbolic world model, so they assumed that we're given this pick and place operator to the agent. But if we, for example, want to like solve a Rubik's Cube, it might like struggle there because it doesn't know how to like move the pieces around. It'll have to learn them. And I can imagine there's a lot of like different robotics tasks where it's not just pick and place, and may require like really like more abstract kind of symbolic, not even like symbolic reasoning. I don't know, like, yeah, so no examples come to mind, but maybe like, you know, for example, like cooking, there's a lot of like, you know, like minor nuances to it that we can't just explain in a PDDL model. So yeah, anyway, like just to sum up that point, like there's a lot of like direction into how we can actually learn symbolic world models to do long horizon planning. I guess another question to think about is like whether we actually need these symbolic world models, because we've seen that LLMs are already like quite well at reasoning in the text space, and they're not really, you know, converting things into a symbolic world model and then solving that symbolic world model, and then using that symbolic world model. They can do everything in text space. But conversely, there are still benefits of these, again, formal languages, because you can, you know, verify them. There are algorithms that exist that solve them with guarantees. But yeah, again, to summarize, like both drawbacks and future work is that we rely on these symbolic world models. We need to learn them, and learning them is hard because we don't know like what's a good symbolic world model to learn.
Yeah. Thank you. And last quick question, and I'll pass it over to you, Alex. So regarding your first paper about planning, I'm just curious how big are these planning problems? Like approximately how many actions do you have and how long is the plan? I'm just not very familiar with these data that you mentioned. I'm just curious, what is the state of the art in planning? How big are the problems that humanity currently is able to solve? Like in terms of number of actions, is it like dozens of actions, like hundreds, or like, and in terms of length of the plan, like how long is the plan and how big is this space of actions available?
Mm-hmm. Yeah, it's a good question. So generally with these symbolic like world model planning problems like PDDL planning, the size of the problem scales exponentially with the number of objects in the problem. And the reason for this is like in these PDDL problems, we have these reusable actions, which are parameterized by our problem objects. So what you can do there is that there are like combinatorially many ways you can instantiate these actions with objects. So if you have like a pickup action with like two variables, and you have like n objects, that's like n squared number of actions that you can generate. And yeah, this scales like exponentially. But furthermore, the state space itself can also grow exponentially, because by similar argument, you have predicates that can be instantiated by objects. And a state is a set of facts, which means that if we want to compute the number of states, this is given by a power set, so like 2 to the power of the number of possible facts, which again can be quite exponential. But anyway, to give like some hard numbers, like some of the problems we solve have like thousands of objects, which can like have like millions or like billions of states and tens of thousands of actions required in a plan to solve.
Okay, yeah, that's pretty good. Okay, thank you very much. So I'm done with my questions, and I don't see any new questions from audience. So yeah, Alex, to you.
All right, very good. Well, first of all, really nice results. And good support of Canada with the moose and bison. Curious on one point where you said in the second set of experiments on bison, there you highlight problems where you said policies are not sufficient, representationally sufficient. Can you elaborate on that a bit?
So second part of the talk, or do you mean the first part, like the purely like abstract PDDL problem?
Yeah, you had
to do search with hidden policies.
Yeah, you had a first set of problems where you showed results and compared to llama and so on, and then you had a second set of problems where you said that policy representation is insufficient. Can you say a little bit more about that difference?
Okay, yeah. So, right, so this kind of idea I'm trying to, okay. So the point here is that like some planning problems are like polynomial time to solve. So that means that there's like either a very simple like linear time algorithm or like polynomial time algorithm that can be simply just represented as a policy where you like given a state, you just apply some action that greedily gets you to the goal. But some like planning problems is quite well known that's to be like intractable or like monotonic, non-monotonic to solve. So there's no like simple greedy algorithm which we can just solve and roll out a policy to solve. Like simple examples, maybe like you can view SAT solving as a planning problems where you try to decide variables to solve in your variables that try to satisfy your kind of SAT formula. And there's no like really polynomial time like algorithm that people know of unless like P equals NP. And that's the point of like why we need search, because we need to like search over different possible combinations of variables that we can assign. And the idea here is like the policy itself that we're like executing itself is like polynomial time to compute. So like theoretically that means that unless P equals NP, we can't guarantee that policies can solve these like NP hard problems. So that's why we need like additional search to solve these problems.
And I think it was a little quick for me, the results here, but can you just highlight the gap again?
Okay, yeah. So again, like just to recap what cumulative coverage means, it means like the number of problems solved in the y-axis within like a certain amount of time in the x-axis. So usually like higher values are better. And with these like NP hard problems, they're like quite like combinatorial and hard to solve. So like usually these problems scale exponentially with respect to size, especially when you're doing search. And like the main first takeaway is that Moose, when we have these additional search rules, can solve like optimal planning problems or like intractable problems faster because you're pruning the search space and you're using like the same planner as the same base planner. So they're both like using the same planner, but like Moose is searching over a smaller state space. So clearly that usually means that Moose would solve problems faster. And this is what we see on the right-hand side. So like Moose usually solves problems faster than the base planner SimK because it's looking at a kind of more pruned or smaller search space. There's one kind of counterexample there, one edge case, which is in this Gripper domain. And the reason for this is that the pruning actually isn't helping that much. And there's like some slight overhead for this pruning operator. So generally this means that Moose is actually not gaining that much from the pruning, but losing some time.
Cool. Okay, thank you. I guess last question since we're close to time. So, the insider track is when we're selecting the problems to show, results on at the end of our paper. Which are the domains you decided not to show because they're a little too hard, or maybe require more generality or expressivity or something. Which another way to ask, what's the kind of hard zone or challenge area for this? Because I think more people should be looking at this general area. So, what are the domains you can't do basically right now?
Yeah, good question. So this relates to, I guess, the future work question earlier as well. So yeah, like you said, there's like some domains where we still don't have like the expressive power to solve using our policy approach. The common answer I give is that anything that requires some transitive closure kind of computation, we can't really do because our policies are simple like horn clauses right now, so they can't really compute like recursion. And one example of where we actually need like transitive closures or recursion is just like, pathfinding on a grid. So if we want like, imagine like a simple grid world, you want to go from one location to the other location. If we train on like grids of size like 3 by 3, our approach can't generalize to grids of like 10 by 10 because it doesn't like extrapolate these transitive closures. So that's one kind of like direction people can look into. The second direction is that implicitly we also assume some kind of decomposability of our goals, in the sense that we can like achieve these goals kind of in any order and greedily, and eventually we can solve the problem. But you may kind of imagine some problems where you have to undo some goals that you achieved to solve them. So a simple counterexample is like this very common PTTL blocks world domain, where we try to stack blocks into certain configurations. So I guess in this domain, you also need some transitive closure computations in order to like tell if a block is stacked correctly and if all the blocks below it are stacked correctly. So yeah, like that's like two directions that we can't handle right now with this approach. So like transitive closures and goals that are more complex and can't be achieved greedily.
Okay, excellent answer. All right, well, thank you so much, Dillon. Jump on Discord if you can, if you have time. And for everyone, one more talk and then a dramatic pause before our summer school, August 6th and 7th. All right. We'll see you all next time or on Discord. Take care, everyone.
Thank you, everyone. Thank you, Alex. Thank you, Olga.